Okay. Welcome back, everybody. I'm here with my brand new pen. Hopefully nothing bad happens today. Today we want to talk about, kind of finish what we didn't finish last time and talk about a few little things here and there to kind of finish the story of all the components that we want to talk about in a real computer. If we have time, then we will talk about kind of like, what happens next and start the story of multi-core systems. Given that you have your quiz next week, I'm also gonna quickly go over your quiz and some of the logistics. Okay. Does anybody have any questions? All right. So last time we talked about how do we schedule things and how do we manage data in my main memory. I said that main memory is essentially a combination of my DRAM and my disk. And we said that essentially the way that we kind of keep track of things is that we define this storage block size or this concept of page, which we said typically is 4 kilobytes of data. And any program that we have, we will divide it into pages, and then we just divide these pages into my main memory, okay? And some of these pages are reserved for the operating system, some of them are read-only, some of them are shared, some of them are writable, and so on and so forth. And the key thing for this page is this concept of page table, because essentially what we can do is we can scatter these pages around the main memory instead of having continuous spaces like predefined static spaces. And the reason, and then in order to fix that issue of, okay, how do we find these different pages? We use the concept of the page table, which basically we translate the address from the user or program domain, which we usually call it virtual address, to what we call a physical address, which is basically the address that the actual memory used in order to address things, okay? We talked about a bunch of different optimization of the page table, like how do we store the page table, how do we improve the page table sizes, and we said basically we can use what's called a hierarchical page table, which kind of like, tree structure instead of like storing everything there. And that was kind of like, how we, how these, state-of-the-art modern machines with operating system typically do that. There are a whole bunch of, how do we initialize page tables? How do we get rid of the page tables and so on, which is a separate topic that, your operating system course will talk about. Question? Operating system is doing what? So the question is the operating system itself being stored in specific places? Yeah, typically. So think about this as the operating system itself is managing the entire memory. So it has its own page tables and so on as well. It might. So the question is, does it change where it stores? It might, yes, because technically it's still. But typically, like some lower addresses or high addresses are standards for being reserved. Another thing that happens is, in order to access things fast, part of the kernel is actually mapped into each different application. So there's some of the pages that's actually being added to each application. But again, we don't go further of like how operating system manages. It's a very extensive topic that in an operating system, of course, you will see how these things are managed. All right. So we said that generally this concept of address translation added this added complexity to our system, because what we have here on the CPU side is the virtual address. On what we have in our caches in our main memory is the physical address. And this translation should happen as soon as possible because things cannot be accessed in virtual world. So we need, in order to do that, we need a concept such as caching. For page table, we call that translation local site buffers, or TLBs. And TLB is basically the first thing that happens when the address comes from the CPU. We will just check our TLB to see whether that address is already cached, that page number is already cached there. If it's cached there, then we have our physical address without any issues. We don't need to go through our page tables to get that address. If it's not, if it's a miss, then we have to go through our page table and do all those things in order to find that data, okay? So, and then after that, we're going to have our physical address, and then we go to our caches, right? So page table, TLB is very important for us. And the important thing is that TLB is, quote unquote, is in the critical path, right? So whichever, data that you want to read, whether it's in L1, L2, or your main memory, it has to go through the TLB. So your hit time is basically, I mean, if it initially was just your L1 cache hit time, now it's L1 cache plus the TLB hit time. So the hit time of TLB is also very, very important in your performance, okay? So this basically is kind of like, graphic of how this happens. And we said that generally TLBs are, I mean, in the past, at least, it was mostly fully associative, very small caches. It has to be small because the hit time should be really low. These days, TLB itself is kind of like an extensive cache. It's multi-level, has set associative, has ways, and all those things that, regular cache also has it. But again, TLB has to be, optimized for search and for hit time because it's within your critical path. So whatever you do with your L1, you have to do it with your TLB as well. We use, similar replacement policies for your TLB. We typically use random or FIFO because, as I said, locality in TLB is less important in locality in your cache because we are talking about 4 kilobytes and 4 kilobytes of blocks. So it's as if that you're doing 4 kilobytes block of your cache. You get less and less amount of locality in bigger sizes, right? And the TLB reach was this concept of how many of these consecutive memory addresses can I quickly, translate from virtual to physical. If I have a bigger TLB, I have a bigger reach, which means that I can potentially work with bigger workloads. Okay? Any questions here? And then last thing that we discussed last time was about the disk. We said that essentially disk is not an additional memory hierarchy for us. We assume disk and memory is kind of combined together. So the same idea of paging applies directly to the disks. It's just that, disk is just much, much bigger memory for us. So if you're assuming that, we have the storage size of M, which M is the addition of DRAM and disk. C, which is for the DRAM, is much more smaller. But D, which is for the disk, is much more bigger. Okay, so typically we're talking about terabytes of data in disk and gigabytes of data in your DRAM. And we essentially said that given that the time it takes for the DRAM to read things is really, really high, you want to be, storing everything, first of all, in your TLB. That's the ideal scenario. If it's not in TLB, you want your pages to be in your main memory. And you really don't want to, regularly go to your disk because that hits your performance significantly, right? And the fact that if your page is not in your main memory, we call that concept a page fault. And in order to fix the page fault is that, for example, you go to it's a specific address, you go to your page table, and you will see that your page table, basically your page table does not, created a physical page number for this. So your main memory does not have this information, this address here, right? So if it's not here, we call that a page fault. And what happens is we have to go through our disk, basically, and find that address, right? And in that address, we need to basically bring that page, and we need to what we call demand paging or swapping, which means I need to kind of find a candidate page in my main memory, in my DRAM, and then evict this page and replace it with the page that I'm bringing from my disk, okay? So the page is there. I'm gonna just put this page here, and I'm gonna evict that the other page, okay? We call this function, we call this activity swapping, because we are essentially swapping these two pages from each other. And this generally called demand paging. So based on the demand, we bring the page to my DRAM. At the beginning, there is no page in my DRAM as we initialize the system. But as you read more things, you bring more pages from your disk to your DRAM. The pages stays there until the operating system decides that it no longer need them. There's no longer demand for them, so just kick them out and bring other pages. You always want your DRAM to be filled with all the pages that you really want. And if you're smart about it, if your operating system is smart about it, then it can find correct, pages and have stored correct pages in your DRAM. Generally, what happens is your DRAM becomes the cache for your disk, right? So all these questions of, okay, what should we bring from the disk to the DRAM? How do we replace, for example, how do we pick which page to kick out from the DRAM and replace it with the page in the disk? What should we do for replacement policies or update policies and all those things? What should be the page size, for example, that we bring? Should we bring just 4 kilobytes, or like memory, we should bring a cache line, for example? So there are all these questions that the same story that we kind of discussed for caches and then for DRAM happens for DRAM and for your disk. And we kind of have to follow the same story as we did for the cache. What happens for DRAM is, for disk is the operating system handles all of these in software. So unlike caches and unlike main memory that we have physical page tables, we kind of hard coded our replacement policy and all those things. We implement all those things in hardware. For disk, things are actually implemented in software. So your operating system decides which type of replacement policy to use. Your operating system stores things, your page tables, and so on, okay? And the reason that we are doing this in software and not in hardware, because it's much more easier, right? But on the other hand, it's much more slower compared to what we did in hardware. Hardware is usually way, way faster than software. But remember, disk, access time for disk was in order of tens of thousands of cycles, right? So it's really, really slow. And your software, your operating system is actually good enough to handle all these things. For caches, we're talking about 1 or 10 cycles, right? So we're talking about nanoseconds latency. That's why you need to implement it in hardware. But when we go to disk, we're talking about milliseconds or sub-millisecond latency, and software can very easily handle all these things. So we don't implement usually things for handling page table, for handling replacement policy and things like that in hardware for disk. Everything is actually handled by your operating system. So again, probably what you will see in an operating system course is things like this, like replacement policy in software and so on and so forth. Okay. Oops. And then in order to know whether this page is cached, is stored in your main memory or not, we typically add this column called valid bits. So remember, for page tables, you have one entry per virtual address, right? So for each virtual address, you have one entry. If it's stored in your main memory, then you make this valid bit equal to 1. So initially, all the valid bits are equal to 0 for every single page table, page table for every single program that you have. Then when you start bringing things from your disk to your main memory, your valid bits becomes 1 and 1 and 1, right? And the way to know that whether this page has been stored in your main memory or stored in your disk is that you're going to go to the page table and you're going to check this valid bit. If your valid bit is equal to 1, it's in your main memory. It's in your DRAM. If it's not equal to 1, it's a page fault. It's in the disk. So you hand it off to your operating system. Operating system will go to your disk, bring that data, put it into your main memory, change the valid bit, and give you the data that you want. It takes hundreds and hundreds of cycles, really, really slow. So that's why you don't want to have page faults in your programs. But it's not something that doesn't you can avoid, right? It happens at least at the beginning of your program. When you're initializing your program, there will be lots and lots of page faults. Okay. Any question here? All right, so this is kind of like, the updated kind of block diagram that we had. Remember, here we start with the virtual address. And here we want the physical address. This memory management unit, or MMU, first goes through the TLB. If the TLB, if the translation is there, then we have our physical address and we are happy. Then we go to our page table and check the valid bit of that address, that virtual address. If the valid bit is equal to 1, then we can find the physical page number and we can go to my main memory and bring it. So I have my physical address. If it's not in the page table, which means that it's stored in the disk, then we're going to have what's called a page fault. Need to go to the disk, and as I said, this is what happened. What is being handled by the operating system. So the hardware tells the operating system that it's not there. Go and bring it for me. So everything has to kind of like wait for this thing to happen. Okay. Any questions? Does that make sense? Good. Okay. All right. So that's kind of story with page tables. All right. There is one last thing that I want to talk about page tables before we move on, and that's the problem of a constant virtual address to physical address. It's good. Virtual address to physical address translation, right? And remember, this is in the critical path of our design, which means that, for every access from the CPU, we need to first translate this, and then we can actually access our caches, our L1 cache, and so on and so forth, right? And this is not the greatest idea because, remember, L1 cache, we want L1 to give us answer in 1 or 2 cycles, right? So essentially what we're saying is that this entire translation should happen most of the time. And then since this TLB is actually, it doesn't have all the information in the word, there will be scenarios that the information is not in the TLB, so we cannot really use our L1 cache in that scenarios, right? So the question is, can we maybe do something with my L1 cache that maybe uses virtual address for addressing? So the idea is what we can do in order to use L1 without translating the address. So basically, we want to use virtual address to access L1. The first thing that you want to think about is, okay, what if we don't translate at all? Like, what if we just directly use virtual addresses in L1? If you remember, we had the problem of what we call aliasing, right? The aliasing was this problem that we said that every program has their own address space. They don't care about the other programs. The addresses start from 0 to whatever number that program needs. And the other program starts from the 0 as well. So it's a very valid scenario where we're going to have, for example, my program A going to have an address like 100. My program B is going to also has the address 100. And my cache will be very, very confused of which one of these is the address that we want, right? So this is a problem of aliasing. So we cannot really, address my L1 cache with virtual address. That was obvious. But maybe what we can do is that we can structure our address somehow that we can access L1 and TLB in parallel. The good thing about that is that, the time it takes, remember our hit time was, our hit time with TLB was the hit time of TLB plus the hit time of L1, right? So it's kind of like serialized. We first access TLB, then we access L1. But if we can parallelize these two, then it becomes the max of these two times. So it would be much, much faster, right? If I can access maybe these two in parallel. So let's see whether we can do that or not. And the idea of parallelizing this is what we call virtually indexed, physically tagged cache. Okay, so how do we do that? The trick is this. The trick is that, remember I said that, our virtual address is basically has two parts. It has a page offset, which usually is 12 bits. And then the rest is my virtual page number, right? And we said that essentially this part does not need translation, does not need to go through page table, does not need to go through TLB and any of that. It just goes completely directly down. We translate VPN to PPN basically. And the address that we want from my main memory is PPN plus the page offset, right? That's the way that we translate this. So we are going to say that given that this part does not need translation, why don't we use this part here to index my cache, okay? And then I'm going to use this part to first go through the TLB, get my physical page number. And if this part is my tag and this part is my block offset and my index, then I can index this physical cache using this address. I can go and bring the tag while I'm translating the VPN to PPN here. So this happens in parallel with I'm going and bringing the tag here. So as I get the PPN, I already have the tag as well. And now I can compare the tag with my PPN. If it's a hit, I already read the data, so it's there. So if you're now thinking about this, all it takes in order to read something from my L1 is the time it takes from VPN to be translated in PPN and compared to the tag. And that's where when we are saying that these two things happen in parallel. Previously, what we had was we first translate VPN to PPN, we get our tag and our index, then we go to the cache and say, okay, let's go and bring the tag and compare this tag with this tag and see if these two are equal to each other, right? That's why it was serialized. So we first access TLB, then we access L1. But what we are proposing is that if the addresses is kind of like, structured this way, that is guaranteed that block offset plus index in my cache is smaller than page offset. For example, in this case, is smaller than 12 bits. Then it's guaranteed that I can always bring the tag just by looking at the page offset without any translation. And then I can continue with my translation in parallel with looking into the data from the cache. Okay. So this way, I'm going to basically my hit time becomes the maximum time for reading this path and this path. So usually it's the L1 is actually slightly, slower than the TLB because it's slightly bigger in some cases. So my hit time then becomes the hit time of my L1 worst case scenario, right? If my TLB is fast enough, which usually is, then we are going back to the first scenario that we talked about, right? Remember we said that our hit time if data is in L1 cache is just T of L1. And now we're back to that scenario, even if we are using the virtual addresses. Does that make sense? Any question? The question is, are we assuming direct map? Doesn't matter, right? So here, We need the index in order to select the row that we want, select the set that we want. Even if this is a set associative, we're going to get 4 tags, right? And then we're going to compare all those 4 tags with my PPN, right? I can compare them all in parallel. So instead of like having one comparator here, I can have n-way comparators, right? It's just the act of going and bringing that data is the one that takes time. The comparison is usually very fast. So this is the terminology that we use. So it's virtually indexed because we are using virtual address to index the cache. So that's why we're saying this is virtually indexed. But it's physically tagged because the tags are still using PPN or physical page number, right? So our tags are still using physical address, but our index are usually are using the virtual address. So that's why virtually indexed, physically tagged. Yeah.
So is the L1 slower in the case where there's a hit on the TLB, or what is the L1 going to be faster?
So the question is, when the L1 going to be faster than TLB? It's just at this point, it's just the time it takes to bring data from my L1 versus the time it takes to bring data from my TLB. It's just what we are saying here. The reason that I'm showing it this way is that, remember, this was the ideal case that we had before. Well, all I'm saying is that if this lookup in TLB is faster than this lookup, if I design it this way, then what I'm going to get as the hit time would be this, right? So that's kind of like a design constraint that I'm going to add. And as I told you, this is not hard to achieve. So we are able to achieve this. But yes, there will be a scenario at which data is not in TLB. So this would be a TLB miss. And then basically our hit time would be significantly higher, unfortunately, because then we need to go to the page table and all those things. So in that case, then this would be TLB plus lots of other things, actually, right? But hopefully, if my TLB is accurate enough, I get lots of hits in my TLB, then the L1 cache hit time is also would be very, very low. Say it again. So what we store in the physical cache, we store both tag and data. So if you remember, my cache was a tag store and data store. And we said that we essentially looking at these two in parallel. So here we get the index. The index is here and here. We look in parallel, so we get the tag and we get the data at the same time. And all we need to do is checking the tag with the tag that is coming from my PPN. I'm going to compare these two. If it says a hit, then I'm going to send this data out. If it's not a hit, then I basically send out garbage. All right. So what would the limitation? The limitation would be that index plus block offset cannot be bigger than the page size. If you look at that, you will see that this means your cache size should be smaller than page size times associativity of your cache. I'm not gonna drive the formula for you, but it would be a very good test for you to kind of see whether you understand CB and S correctly. So if you plug the numbers, you will see that whatever your page size is, dictates what is the size of index plus block offset is. Associativity and cache size basically tells you those two numbers, and you will see that basically what we're saying here is that block offset plus index should be, for example, less than 12 bits. If it's more than 12 bits, then this doesn't work, right? Because you need translation. So rest of your tags, your L2 and L3, what they are they virtually indexed, virtually tagged? Are they physically indexed, physically tagged? What are they? Any suggestion? What is your L2?
Everything should be physical after that.
Yes. So everything is physical. So your L2 and L3 is physically indexed, physically tagged. Okay. So the default is everything is physical, except your L1, which is the virtually indexed, physically tagged. Okay. All right. So that's kind of it with virtual addresses and main memory. One thing to keep in mind is that virtual addresses is not something that exists in all the systems because it requires lots of storage and requires lots of power and energy. So there are lots of the large class of devices actually do not have a memory management unit. They just use physical addresses. In that case, you will go with that static partitioning that I described at first. So like, devices such as embedded systems, low-end processors and so on, they all just use physical addresses. They don't use the notion of virtual addresses. Virtual addresses is something that's used in more high-end systems. I mean, these days, your cell phone and your iPad and your PC and your laptop using virtual addresses, but there is devices, tiny devices that don't use virtual addresses at all. Okay, so just remember that this is not something that every device is used. Okay. Any final question about virtual addresses and main memory? All right. So now let's talk about other things in our system. So we kind of talk extensively about processor. Now we kind of know what's going on with my memory. Let's see what other things actually there, and let's quickly talk about those. So other components in my system, other than the memory and processor, are generally referred to as I/O or inputs and outputs components. And inputs and output components are actually quite important for us because without inputs and outputs, you have no idea of what's going on in your systems. And there are lots of inputs and outputs that you use. This pen, this the screen, the keyboard, your mouse, your printer, and all those things are technically inputs and outputs. Something happens in your processor. It writes things and reads things from your memory, but at the end of the day, it should show you something as the user who interacts with it, right? Sometimes it shows it to you as a user. Sometimes it's some form of actuation. For example, there's a step motor that something happens, then step motor moves. The elevator, change this, the floors and so on and so forth, right? So there is some form of actuation that happens as a result of your activities in computers, and typically there is some inputs. There are some sensors that kind of get those information, right? So for example, I click on this next slide and it goes to the next slide, right? So this is kind of like a command that translates into some inputs, goes into the operating system as an event. The event will be translated in a bunch of programs, a bunch of applications, or a bunch of instructions. The processor will run it. There will be some results written into the memory. Then the results will be sent back to the operating system. I'm going to see that, oh, okay, my slides actually changed from here to there, right? So this is basically the I/O. And if you look at the structure of the computer, basically your structure will look like this. You will have your CPU. Typically, CPU and caches are in the same chip most of the time. So there is a dedicated channel between your CPU and caches. Then you go into what is called a bus, which bus is essentially a line that everything is connected to it. And it's kind of like, one at a time, information is being sent and received, okay? Typically, we have what's called a memory bus, which a dedicated channel between your cache and your DRAM. And then this is also connected to some form of a controller, which we usually call, I/O controller or I/O bridge. And this I/O bridge is then connected to a bus with all these other I/O devices that are connected to it. So your keyboard, your LAN, your display, your GPU, any other things that you have, all of them are connected to this bus. And then they send and receive with some, protocols to this bus. This bus gets this information and eventually send and receive it to the CPU, or as we will talk about, directly talk to your DRAM. Okay, this bridge is what is kind of like, kind of like abstract away your IO is also for some electrical purposes. You need to have a bridge, because if you add more and more things here, the electrical characteristics of your bus changes. So it kind of wants to isolate that from your processor side. So that's why you have what's called a bridge. Okay. So this is kind of like the structure that our computer has. Bunch of IO devices, and you can keep adding IO devices if you want. And then you have your DRAM, you have your CPU, and you have your cache. Okay. And then this type of IOs depends on the class of devices that you're using. The IOs that we have in the cell phone is very different than the IOs that I have in this PC, than the IOs that you have in your laptop, right? So for example, we will have, secondary or ternary storage units, including like flash and so on. Network is big part of the IO, like, LTE, Wi-Fi, Bluetooth, and all those things. The HCI interfaces, including your mouse and your keyboard, your touch screen, audio, video, and all those things. Printers and sensors and actuators, all kind of different IOs that we might have in a system. And as I said, depending on what class of devices are we using, some of these IOs might be there and some of them may not be there, right? So the question now becomes, how do we read and write to the IO from the CPU perspective? Because CPU needs to kind of communicate with the IO in some sense as well. So how do we actually do that? We kind of now know that, if a load or store comes in, we know that we need to go to your main memory. But how do you know that, for example, you need to read from your keyboard? How do you get that information? So there are two ways that you do that. The simplest way that you will probably see in your, microcontrollers or Raspberry Pis and so on and so forth, is when you have a dedicated channel or dedicated registers. If you, for example, play with like, devices like Arduino, you will see that there are like, GPIO ports, like GPIO 0, GPIO 1, so on and so forth. These are specific input output ports that your register under your CPU understands them. And in your code, you can actually, code it and say, okay, read this LED or read this value from my GPIO, or write things to my GPIO, and so on. These are effectively translated into registers, okay? So the same way that we have like X0 to X31, we will have GPIO registers, like GPIO 0, 1, 2, 3, and so on and so forth. And interaction with your IO would be writing and reading from these registers, okay? So I'm just like, if I want to store, write something, if I add, for example, just GPIO with X0, I'm effectively writing to that specific port, okay? So this is like, dedicated channels. Typically, we'll see this type of dedicated channels or registers in microcontrollers, in FPGAs, and in low power or resource constrained devices, okay? In more advanced systems, we will typically use what is called a memory mapped IO. So the memory mapped IO is this trick that we're gonna say that, IO for us as processors is just another address in the memory. So for example, we can say that, this is my memory. This is the address 0, for example. This is address, I don't know, 1 million or whatever, 100. What I can do is that, okay, now maybe I want to add 32 more ports to my IO. What I can do is that I can say that, okay, I'm gonna extend my memory, think that I'm extending my memory, and say that, address 101 is for my keyboard. Address 102 is for my mouse. So instead of having registers, I'm treating my IO as what's called a memory mapped. I'm thinking that whatever data that's been written to address 101, or whatever data that's been read from 101, is what is like written and read by the keyboard, okay? So basically, reading and writing to IO becomes same as store and load. The addresses just changes, okay? And the operating system can handle this for us because whenever you install a new IO, there will be a dedicated address for it. The operating system knows that. And whenever you want to write things, for example, to your keyboard, the operating system will translate that address to the address that you want, and it will read it and write it from that, okay? The important thing is you don't want that data to be cached. The reason that you don't want it to be cached is you keep reading and writing from it, right? And caching this way doesn't help. You don't want to have the cache information here. And how do we do that? We typically use page tables. And remember, in page table, we had a bunch of flags, right? We said that, there are these flags next to each of these rows. Here, we can maybe have one bit of like, whether this is cacheable or uncacheable. And for example, we say that this one is uncacheable, which means that, whenever we see this, just ignore the cache, just read and write directly from it. As a result, reading and writing from your IO is very, very slow because it's same as like, going through your main memory and reading things from it, even worse than that because it has to go through the bridge and through the bus and so on. That's why you cannot really type things in order of nanoseconds. If you type something, you will see that there is millisecond takes, even in modern processors, to like, see the characters, right? It just has to be fast enough for the human eye to not detect the delay. But it's not in order of nanoseconds as we do read and write things from our cache. It's in order of milliseconds or even less, all right? And then you can have virtual addresses for this as well. As I said, from the CPU perspective, you might define keyboard with some specific library that you use from the operating system. The operating system will handle the addresses for you, okay? So whenever you want to write to your keyboard or read from your keyboard, that's the operating system jobs typically to handle this for you. If there is no operating system, then the memory map should be a static address. So for example, you should know beforehand that my mouse is at this address X. And when you're writing your program, whenever you're writing to that address, that physical address, that's when you're writing to your mouse or reading from your mouse. Okay? So that's the technique that we use in order to read and write from your IO. Any question here? Yeah. So the question is, why can't we cache this addresses? Because you don't want to cache this addresses, right? Because you're reading something from that data, you typically store it in some registers and you move on. You don't want to, change, because if something changes in your IO, you want to know that this has changed. So that's why you always want to go there. Because for example, if I change something in my mouse, there should be a mechanism for me to tell the cache data that this has changed, right? There is no mechanism for that usually because the IO does not have access to my cache. So you don't want to store value in the cache. Okay. Yeah. So you basically, you read things, you do something with it, you reread another thing. If you want to reuse that, the best idea is just store it into some temporary variable or some memory and use that. But you have to just know that during that process, something might change and that data won't get updated. So it's your responsibility to update that. All right, so if you remember, I told you that, basically we have our CPU, we have our main memory, and then we have this bus, and then basically all these IOs are kind of, connected to this bus. This bus is, think about it as a wire that kind of multiplex between these requests. And typically there is 3 players in this. This controller is what we call an arbiter. Then any of these, IOs are either initiators or the targets. So for example, if you have a network, Wi-Fi network that gets a packet and wants to send this packet to my CPU, the Wi-Fi IO becomes the initiators. It has to tell the arbiter that oh, I have some data I want to send, but there could be some other IOs that also has data. And since all of them are sharing this bus, we need to kind of like, having kind of like a scheduling mechanism. So think about it as kind of like a stop sign, like, a junction that multiple cars comes in. And there should be like, a schedule, like you go first, and then you go first, and then you go next, and so on. So the arbiter is typically a logic that it, implemented inside my IO, typically on the bridge side, that tells each of these IOs who is now can, send their data. Okay. And the other way around is also possible, right? The CPU has some data and wants to update one of these IOs. Again, the arbiter says that, you know what, Wi-Fi IO, you are receiving this data now, so be ready. And then it's going to send that information. So there is typically some form of, connection between the arbiter and each of these IOs to send and receive some control signals. And then all of them sharing this bus data, that's basically their send and receive their data from. Okay. And we have different standards for IO. So not all of them use the exact same standard, not using the exactly same data rates. So in reality, what we have is something like this, where we don't have one bus. We have multiple bus with different speeds. Okay, we have a fast bus, we have a slower bus, we have much slower bus, and so on and so forth. So if you have heard about terms such as PCI or PCIe or Ethernet or SATA and all those things, these are different standards for IO. And the main difference between them is how much information they're sending, how fast they can send this information. So PCIe, for example, we're talking about gigabits of information being sent and received. And that's useful for things like, fast connection, fast Ethernet connection, fast GPU computation, and so on, that you want to read and write things very, very fast. But on the other hand, you don't want to read things fast, for example, from your keyboard. So it's better to use IDE or PCI for those kind of connections. So there is various, ways and lines for connection between the IO and your CPU. The main difference between them is the standards, the technology, and how fast they can send and receive information to each other. And typically, there are a bunch of them in your motherboard. So typically, you will have your CPU sits in a big motherboard, and then the CPU is basically connected via a fast connection into multiple of these different slower connections. Some of them are, for example, very fast. Some of them are like, medium speed, and some of them are really, really slow. Because in some cases, you want fast connection. In some cases, you want slower connection. And the reason that we just don't use fast connection for everybody is just, use powers. You don't want to do that, right? So you kind of like, balance between the speeds of your connections. Okay? And then another thing that I want to say before moving on to the next step is this, sending and receiving information between your arbiter, initiator, and target could be either synchronous or could be asynchronous. The asynchronous one is when we don't have a clock or specific timing. It's more of what we call a handshaking protocol. That, for example, somebody says, I have data. Then it waits. Then the arbiter will initiate that connection. Say, okay, I'm ready to receive your information. Then the initiator will say, okay, I'm going to send you 8 bytes, and I'm going to say, I send you 8 bytes, and wait for you to acknowledge that you have received 8 bytes. Then I'm going to send you another 8 bytes, and so on and so forth. So first 8 bytes might take 2 seconds. The second 8 bytes might take 3 seconds, and so on and so forth. I'm going to send you things, but the way that I'm going to send you is that, like, I'm going to wait for you to tell me that you have received it. Then I'm going to send you the next one, and next one, and next one. Okay? So that's usually what's called an asynchronous type of, communication. The synchronous one is basically saying that I have data, and you say, I'm ready to get it. and you're gonna just send it. You're gonna send it with specific timeline that we agree on. So there are multiple different protocols like SPI or I2C or these different techniques that all of them are basically saying that we're gonna have a shared clock, and we're gonna assume that, for example, in the first cycle, I'm gonna send you, for example, start bits. Then I'm going to send you data for the next 8 cycles. Then I'm going to send you maybe 2 stop bits, and so on and so forth. So there is a standard that you have to read. I'm sure most of you already know many of these standards that basically they share the common clock, and they basically just sample data at each positive edge of the clock. This is much more faster, but much more difficult to to get, because if there is like, it's even smallest amount of, discrepancy between the clocks of these 2 devices, or for some reason one of them gets out of control or gets unavailable, there is no way that these 2 know, right? So there will be lots of errors because of this. Versus the handshaking one, the asynchronous one, is guaranteed that you always receive the correct data, but it's much more slower, right? You have to wait for the data receiver to acknowledge it, then send it, and so on and so forth. Okay, there's a whole bunch of stories and research and how to make these data protocols faster. It's a story of a different course, obviously, but just have an idea that this is possible. Okay, any questions? Let's have a quick break, and then I'll talk about DMA next. So another thing that we do for our I/O is what's called a direct memory access, or direct DMA. Okay, DMA is this idea that our IOs can talk directly to my CPUs, right? And we use that, for example, using memory map IO, using the arbiter, and so on and so forth. The question now becomes that if IO wants to write something to my main memory, right, what should we do? What we have right now is that the IO will say that, what, I have data. The arbiter will tell the CPU, and the data starts, flowing from my IO to my CPU. And then if you want to store things, the CPU has to go through the same cache hierarchy that we talked about and just issue a bunch of stores in order to store things into the main memory, right? And this is very inefficient, obviously, because in many scenarios, what we want to do is, for example, reading a file or opening an image and all those things from a camera. So there's a stream of data from my IO, and that stream of data needs to go to the memory directly, because we cannot, process all this on the fly. So in order to fix that, instead of like taking this path of from IO to the CPU and from CPU to memory, maybe we can add this additional logic here called direct memory access, or DMA, which this DMA is basically sits next to this arbiter. And if the IO says that I have this data, but I want to write it into my memory, we're going to create a path between the IO and the memory using this DMA. Okay, so DMA is basically this kind of semi logic that we put in our IO ecosystem, that if the IO wants to write something directly to memory, which is very common, instead of going through the processor, but maybe just initiate that, oh, I have this data and I want to write it to the memory, the CPU will tell the DMA to just handle this for me. And the DMA is basically just reads the information and directly writes it into my main memory. Okay, so that's what the DMA does. So this is just, description of what I said. So the DMA is an engine that offloads the CPU's work by directly transferring data from the IO to the main memory. Okay, and DMA is basically just get the initialization command from the CPU, and they will tell the CPU that this, communication, this offloading has been done, and it just notifies the CPU that this happens. All right. And basically, the DMA could be something very similar to all these other memory mapped IOs. So in order to send and receive commands from the DMA, the CPU can use memory map registers and say, okay, this is the register for DMA, send things, receive things, and so on and so forth. Okay. DMA itself, since DMA is kind of having some form of a controller, there's a tiny bit of processors inside the DMA itself. A processor inside the DMA is something that's very simple, that can only run few instructions and so on. Think about it as a mini processors that we have for the DMA with a list of just only a few commands and few instructions that needs to run. Okay. And then the interesting thing is that there might be multiple of these DMAs. So there's not just one DMA, there could be multiple DMAs in the system, especially modern systems typically have multiple of these. Okay. So this is kind of, the updated version. As you can see, there is a DMA, for example, here, but we can have, for example, a DMA for the graphics unit. We can have a DMA for this particular IO devices. These slower ones probably don't need DMA because they don't have much information to send anyway. But this faster one, since they have lots of information, they probably need a DMA. Okay, so this is basically what we're going to have in the modern systems. We will have a CPU and caches. We're going to have a DRAM. We're going to have a graphic unit, a GPU. The GPU typically has a DMA. Then we're going to have a whole bunch of IOs. And by the way, your disk also sits somewhere here. So one of these IOs is your disk, right? Maybe this one. And then there will be slower IO bridges and buses, and there will be faster IO buses as well. And you can just extend this as much as you want, as much as your motherboard is basically support this. And this is basically your kind of like, your motherboard. So this is your motherboard. Basically, motherboard is your is a printed circuit board that has these components and has this logics and buffers and all those things. Okay. Any questions? Awesome. So now the final question about the IO and the systems is, how do we notify the processor that we have something? We said that there is an arbiter that's kind of like directly talk to these IO components, but how the arbiter says to the processor that I have something, okay? There are two main methods that we typically use. You probably already know that. There is an interrupt and there is polling. So interrupts occurs when there is an event, right? So we usually says that in any processor, in any systems, there is list of events. And for each event, we have what's called an interrupt handler or a service routines that if this happens, do that. If that happens, do this, and so on and so forth. So what happens with the interrupt is typically, think about it as a pins in your CPU. So your CPU have a bunch of pins. And if this pins becomes 1, it's, for example, when we have this particular interrupt. So the CPU does its job, doesn't have to be worried about external events that is happening. As soon as something comes up, this, for example, pin gets high. If this pin gets high, then the processor knows that something is going on. There is some IO that wants to send me something. Then the processor can decide when it wants to service that interrupt. It doesn't have to be, instantaneous. It can wait for some time and then decide to do that. So the good thing about this is that there is no overhead to the CPU side for checking what is going on. But the problem is that if you want the interrupt to be serviced, instantaneously, then, for example, if you're in the middle of, computation, if the interrupts comes in, your execution will be interrupted and you have to go and service that request, right? So there will be, overheads because you have to kind of save things that you've done, jump and service that routine, and then come back, right? So if you design your system such that as soon as, for example, this positive edge comes in, I have to service that, then there will be problems, right? Instead, what you can do is that you can say, okay, I'm going to just check whether or not I have something whenever I see fit, whenever I feel that I have nothing else to do, and then I can go and check. This is typically called polling. I basically, run some of the things, part of the program, let's say. I run partially part of this program. Then I'm going to say, okay, now it's a good time to go and check whether there is any new data to come, right? If it's not, then I'm just going to continue. If there is some information, then I'm going to pause this, execution. I'm going to just run this execution here, and I'm going to service that request here, right? It's the same way that we are handling this class, right? So if you have a question, you will raise your hand. That will be an interruption. But sometimes I also say, when I go to the next slide, I stop and say, is there any question? So I'm doing the polling and you doing the interrupt, right? And that's kind of like the way that we are handling questions, right? Same story for the CPUs. The problem with this is there is an additional overhead to the CPU, because the CPU every once in a while has to go and check whether there is something that needs to be serviced. So on the interrupt side, we just don't care. We just continue doing that. Whenever somebody has something, we will be notified. Versus for the polling, there is a service routines that needs to be executed. But the good thing is that it can be fully scheduled. So I can just focus on computing and completely ignore anything else if I want to. And then when I see fit, I can go and do the polling, right? So there's kind of like, a trade-off between those two. And typically what we use in modern systems is what's called a hybrid, solution, which we essentially say that for the first event, for example, if I want to read something from the Wi-Fi network, from the access point or whatever, I'm not going to go and check every time that do you have anything for me or not. I'm just going to do my thing. The first time that there is a packet, the access point going to send an interrupt to me, and I'm going to go and service that. The next time, say that, okay, it's probably, if you have one packet, very likely you're going to have more packets for me in the next few seconds or so. So don't interrupt me anymore. I will come and service you whenever I want you. Okay, so the rest of the services will be basically polling based. Okay, and then I can switch back to interrupt after a while. So I say, okay, I've seen all the packets that you have sent me. Now switch back to the interrupt. Whenever you have something more, just interrupt me if you want. Okay, so it's kind of like, the idea of the hybrid methods. Typically, most of the things that we use in our modern systems kind of this way. And again, this is something that, operating system typically handles. All right, so, handling the interrupts and handling the IOs is one of the key jobs of the operating system. If there is no operating system, then it's the firmware's job to handle this, right? So you have to kind of like have a mini kind of piece of code that's kind of act like that for your codes. For example, again, if you're writing some microprocessor coding, if you have done it before, you will see that you either use interrupts or polling or a combination in these cases. Now that we talked about the interrupts, let's talk about two other things that are kind of relevant to the interrupts, and that is exceptions and traps. So exceptions are when something unusual happens in your system, right? So you're running a program and then something unusual happens, all right? So for example, you're trying to read part of the memory that you're not supposed to. You are dividing by 0. You are, for example, do a misprediction. You do, you don't do raw data hazard correctly, and so on and so forth. So exception is these kind of events that happens, and these are the events that you want to avoid, but sometimes they happen, right? So we are calling it exception. There's a long list of exceptions in modern systems. A few of them I just explained. The trap is the act of kind of servicing the interrupt or servicing the exception. Okay, so what happens is that you have a bunch of instructions, right? And you start your processor start reading these things. And then an exception happens somewhere. For example, a misprediction happens. What should we do? We should basically execute what we call a trap handler, okay? Which is, think about it as a sequence of instructions that instead of running this normal instructions, we are running those sequence of instructions. For example, remember for branch misprediction, we have to kind of clean up the ROB, we have to clean up the RAT, we have to change the PC back to something else. So that itself is a program. And trap meaning that, we're jumping to that handler. So we have to first see what was the exception. For example, is the exception was branch misprediction, or was it divided by 0, or was it something else? And then trap is basically saying that, take the control flow from this set of instruction, change the PC to something else. So basically, I changed the PC and pointed to somewhere else in my memory. And remember, I told you that there are some places in my memory that is reserved for the operating system. Part of it for these trap handlers and for these interrupt handlers, okay? So we basically jump there. That's a program stored there. That's kind of tell us what to do for this specific exceptions. This exception, for example, has typically an IDs like 00 for this, 01 for that, 02 for this, and so on and so forth. So we go to that specific address. That's the beginning of a program. We're going to run that program, which is basically tell us what to do. Once we run that and execute that, we fix that issue, then we can jump back and continue our execution. Okay? So this is kind of like, the way that we handle these things. And as I said already, interrupt is this external events that happens asynchronously, obviously, from our execution. Typically, interrupt can be assumed as one type of exception. So interrupt is kind of like, special type of an exception. And when an interrupt happens, we trap the processor again. We jump into what we call an interrupt handler. And we're going to see which interrupt is this. So we're going to run things. Our PC is here. Then an interrupt happens. So my PC will change from here maybe to like later down somewhere here. And here I have list of interrupts. So for example, if GPU sends me something that's 00, if keyboard send me something that's 01, and so on. So I'm going to jump to that specific program again, going to handle it, get the data out. Then I'm going to go back to this PC plus 4 or PC plus 8 or whatever it was and continue the instructions. Okay, so this is kind of like just kind of connecting to the story of the PC and the main memory. That's how we are kind of handling the IOs and the requests and the misprediction and all those things. Okay. So again, some of the examples is like branch misprediction. This cause an exception. We need to kind of like handle it by jumping into part of the program. Something to remember, there's this notion of what we call a precise exception. The precise exception is when we want to, recover all the necessary states in our program. So there's a slightly difference between what we call the precise exception and regular exception. For example, for things like branch misprediction or any sort of like issues that we have with the execution of instructions, we want to have a precise exception. So it's slightly different than how we handle the other type of exceptions. I'm not going to go through the details of that. Again, that's related to your operating system course, but just keep in mind that there is this. The IO events typically create an interrupt, and as we said before, the interrupt is a special type of an exception. The interrupts themselves have priority. So if there are a bunch of interrupts happening together, we typically have a priority over which one is more important than the other. And we typically first handle the first one and then handle the second one and handle the next one. Sometimes we call interrupt masking. For example, we say that for this amount of time, I'm not going to care about some of these interrupts. So for example, I don't care about whatever you do with your keyboard if I mask that interrupt. Okay, so there is typically, a priority list that we need to care about for interrupts. And then system calls are also kind of like, an examples of a trap. So for example, if you write your program and then you have cout or printf, this is basically a function call which jumps into somewhere else in the main memory that is handled by the operating system. This is usually what we call, it's a call, but it's called for your system's application, systems function, not your regular function that you've written. This is kind of like it's similar to the way that we are handling other traps. The PC changes to that, whatever that address is. So for example, your cout is actually a program itself that's stored somewhere in your main memory, typically is stored at some reserved part of your main memory, right? So whenever you have a cout, let's say you have instructions here and your PC is kind of like, pointing out here. When you have the cout, what will happen is that the PC will be transferred from here to the beginning of this function wherever it's stored, right? Again, the operating system knows where this address is. It's going to change your PC there, going to execute those instructions for you. You're going to print something into the IO. Then you're going to get the results back and just continue execution of your system. Okay. There's also a whole bunch of other examples, like an unknown instruction, for example. What if you just do something weird in terms of the instructions that doesn't support your processor? Failures and overflows and all those things are all different types of exceptions that might happen in your system. Probably if you Google, you'll see a long list of these exceptions. Usually there's standard for each one in each processor. So for example, RISC-V has its own set of exceptions, x86 has its own set of exceptions, and so on and so forth. Okay? Any questions? All right, so this is kind of like, what we call a system on a chip, right? So this is kind of like all these things that we kind of talked about. This is an SoC for a TI processor, and you see lots and lots of things going on. So we have, for example, our cores here, and in this case, it's a multi-core. You'll see that there is difference between different cores that we will talk about. Then we have like, our L2 cache, we are memory manager. Then we have whole bunch of, processors and DMAs. Then we have a whole bunch of, these IOs next to it. We have this I2C protocols. We have this keypad and PCI protocols. We have UART and GPIO protocols that maybe talks to some keypad, that talks to maybe some, I don't know. What else do we have? You have like, USB here. So there's a whole bunch of, complex inputs and outputs, components that you add to your system. And what they are at the end of the day is this technologies, this IO pins and ports that connected via some methodology that we discuss to your processor at the end of the day. And that creates this complex systems that we are dealing with in your cell phones, in your laptop, and so on and so forth. Okay? And hopefully now you have a very good understanding of all these components, kind of like the way that, instructions are being executed and so on and so forth. Okay? And I want you to kind of like, remember, like, have a general idea of this kind of like, flow, right? So of course you may not remember the details of your caches, but what you should remember is that there is kind of this structure in your computer, and this is kind of like the flow that we do. Okay? Any questions? All right. So that's kind of it with the designs of all the components. The last thing I want to discuss in this course is where we are right now and what is like the last thing that we added to take us to 2022. right? So if you remember, we said that, we showed this image to you long time ago, and we said that there are a bunch of, technology and computer architecture techniques. And the whole main things that we talked about so far was all these techniques. We talked about speculation, out of order execution. We talked about caches. We talked about IOs and so on. And we said that there were somewhere in early 2000 that we added all these features to our system. And unfortunately, at that point, we saw that we can no longer make this faster because of the temperature and power constraint. But we basically what we call hit the power wall at that point. Okay. What happened next? If you remember, I told you that that's what we call the era of multi-core. So we saw that instead of improving the performance of single cores with adding more and more things to it, we kind of adding more and more cores to our system. So this core gets bigger and bigger and bigger and better and faster. At some point, we couldn't do faster processors. So what we do is that we kind of replicate this into 4 cores or 8 cores or whatever. And we're going to say that if we can divide our work into 4 pieces, and each of these 4 pieces can work synchronously in lockstep and can run things faster for us, technically the number of cores that I add to my system, that many number, that's how much faster my computer gets. Okay. So we want to now talk about that idea and see what is that idea, how do we do it, and we're going to see 2 major issues that we're going to face when we start doing this. Since we are sharing information between cores, now we're going to have what's called a coherency problem and a consistency problem. And that's the story that I'm going to talk about in next lecture next week. Just going to talk to you a little bit about both. So what we have right now so far is what we call a uniprocessor, right? We have the notion of threads, which basically each of these programs are basically becoming a thread. We have a PC and register for each thread. We have a stack for each thread. We have heap and globals and all those things for each thread. And basically all the threads share the same memory space, right? So we have a bunch of different programs. They use the shared memory space. Then we have a notion of process, which is kind of like, a level above the thread. And that's when we have, each one has their own memory, virtual memory. They think that they have access to entire memory and so on and so forth, right? And typically, in order to run multiple things in our program, we use this concept of thread scheduling, or the operating system kind of like manage this for us. So if you have a bunch of different applications in your program, in your computer, we will have what is called a context switch that we run this for some time. Then we just remove this, run the other one, take it out, run the first one, and kind of like context switch between each of those 2, right? And in order to do that, we typically use interrupts. So we say, okay, you run for like 5 milliseconds, then send me an interrupt, stop, you run for another 5 milliseconds, and so on and so forth. So that's the story of what we have seen so far. But what we can do is kind of like, to improve this a little bit more is we can use this idea of what we call a simultaneous multi-threading. So what is that? So remember we said that in order to make things faster, we use ILP, or instruction level parallelism, right? So at first, one lane of code, execution, and to our pipeline, then run I2, send it to the pipeline, and so on. Then we said that, okay, why are we not duplicate this? And we gave you the idea of superscalar, right? We said that essentially, let's have 2 fetches, 2 decodes, 2 execution, and I1 and I2 goes together, right? And we said that if we can actually use our pipeline efficiently, we get 2 times faster execution, right? Bunch of instructions together in parallel we get what we call ILP, or instruction level parallelism. We parallelize instructions together, we get more performance. With out of order, we get much more performance because we can run things out of order, so we can always find candidates to put this into our superscalar processor, right? What we can do further is we can extend this idea to what we call a thread level parallelism. Why do we want to do that? Because even if we are using out of order execution, because of the memory latency and because of poor branch prediction and because of the data dependencies, not all the time all these processor lines are going to be full. If you recall your homework, for example, there will be a scenario that you have available lines, but you just have to wait for example, the memory to come back so that you can run the next one, right? So even if you have out of order execution, because of the dependency, you may not use all those. Or if you, for example, make a wrong decision about your branch, even if you execute lots of things, you have to just ignore all of them and go back and rerun things, okay? So what we can do is kind of like, improve this a little bit more is if you look at this, for example, if we have like, a bunch of functional units, so this is time and this is the number of functional units, 1, 2, 3, and 4. And this kind of, darker color means that this functional unit is being used. You will see that because that you either have dependency or you have misprediction, not all of these functional units are being used. So at this point, we are happy, but these are the ones that are not being used, right? Sorry, these are the ones that are being idle. So what we can do in order to further optimize this, we can not only interleave instructions, but we can interleave programs into my functional units, okay? So for example, if I have a program that this one, and this one is being used, and another program that's, have a bunch of them used here, a bunch of them used here, what I can do is maybe having this 4x4 functional unit, and then say that, okay, these two is for program 1, and these two is for program 2. And now that I have more options, same way that we had more options for more instructions in out of order, I can just put more things into my functional units. And hopefully this time I have enough of these, I can always utilize the 100% of my system, because now I'm adding more and more programs, more and more options, more and more candidates to my system, right? So this is what's called a simultaneous multi-threading. So multi-threading means that we have multiple threads, we have multiple programs in the same pipeline at the same time. Remember, so far we said program 1 just run things. We had a bunch of instructions for program 1, put it into superscalar, but we never said that, okay, maybe you have program 2 as well. Maybe 2 of those instructions can go inside your pipeline. So now what we are saying is that simultaneous multi-threading, or SMT, give you this option that basically you can just read all these instructions at the same time. And instead of like saying that, okay, I'm going to just focus on program 1, maybe you can focus on program 1 and program 2. And these are completely independent programs from each other. There's no dependency among them. There's dependency within each program, but there's no dependency among the programs because there are 2 separate. So X1 in program 1 is not same as X1 in program 2. These are separate programs, okay? So we are basically with SMT, we are saying that I have more options. Maybe I can, feed my functional units more, okay? But of course, this comes with additional storage area and additional overheads, because I cannot use the same register file for those 2 programs, because as I said, X1 in program 1 is different than X1 in program 2. So I need one register file for one program and another register file for the other program. I need to rename one program differently than the other, so I need a different RAT. The ROB doesn't matter because I can just keep track of ROBs at the same time. But essentially, many things actually becomes duplicated. Same way that we duplicate things for simple scalar to superscalar. If you remember, we said that basically our registers becomes like 4 outputs instead of 2 outputs. Now I'm saying that, your register actually has to be replicated and be 2 outputs. Because this is register file for program 1, this is register file for program 0, right? So many things has to be replicated because of this SMT. And again, you will, same as you had 4-issue superscalar, you can have 4-issue SMT. You cannot have arbitrary number of SMT. But if you have small enough of this, then you get a significant performance boost in your system. Okay. So I'm going to skip the example, but I already show you. So your fetch basically becomes fetch of 2 different programs. So you have PC for program 1, you will have PC for program 2. Then you get, your decoding should be decode for this program, decode for that program. Then it goes to rename, so it has to go to RAT for program 1 and RAT for program 2. And the story kind of continues, right? So there are many cases that you kind of need to duplicate this. And if you're doing 4-issue simultaneous multi-threading, then you have to have 4 of these together. But again, we can't afford this because the processing was, the real estate in hardware was cheap at that time. And that's kind of like our last try in order to make computers faster, our uniprocessor faster, okay? And one thing to remember is that context switching and multitasking are 2 separate things. Context switching is basically saying that I feed one program into my pipeline. I'm going to execute that for some time. At some point, I'm going to pause that. I'm going to what's called a context switch from one program to another program. The context switch usually means that I need to store my register files, my PC and inputs and so on. I'm going to store it somewhere into the memory usually. And then I'm going to restore the other instructions. So read from memory. And then at this point, I'm going to start executing program 2, right? SMT tells you that, you can run both of them at the same time. You just have to duplicate your storage for these 2, okay? So you can have both SMT and a context switch at the same time if you want to, all right? So nothing prevents you for doing that. So this is kind of like, a summary of what SMT is, okay? So in conventional systems, let's say, for example, you have functional units 0, 1, 2, and 3, and let's say green means that it's being used. So in each cycle, you have a bunch of them being used for one thread. Then you're going to have context switch, and then you're going to run your next thread, right? Then on the other extreme, you will have what is called an SMT or simultaneous multi-threading, which you basically have, for example, 4 different applications. You're going to have green, red, yellow, and blue. And you're going to say that at each point, whichever has available instructions that goes to the functional units, I'm just going to put it. And if you compare these 2, you will see that this one almost always we kind of like, use all the functional units all at the same time. There will be scenarios that we cannot feed anything. That's normal, but we are basically talking about like, 90-ish% utilization with simultaneous multi-threading, okay? Another thing that we can do is what we call a coarse grain and fine grain multi-threading. So the idea here is the coarse grain one says that I don't need to context switch. What I can do is just run some program for some time, then run the other program. So I still have, for example, register files copied, but I just don't run them at the same time. So my scheduling getting a little bit better than SMT, but I just run some program for some time, but I don't pay the penalty of context switching. Okay, because I replicate the hardware, I just can quickly switch between, for example, thread 1 and thread 2 and thread 3 and so on. Then there is fine grain multi-threading, which means that I can basically switch between each thread, within one cycle. So in cycle 1, I can do this. In cycle 2, I can do this. Cycle 3, I can do this, and so on and so forth. Slightly better than this one and this one, because in each cycle, I have 4 different options, and I can pick the option that is most efficient for me. And finally, the last extreme is what most of the modern processor use, is that we do what's called a simultaneous multi-threading, or SMT, which we're going to say that not only in each clock, but within the same clock, I can just run things together. Okay, so this would be what your functional unit will see. All right, so that's what you will see in your uni processors these days. You're going to have out of order, you're going to have simple scalar, super scalar, sorry, and you're going to have SMT, because you can run multiple things at the same time. This is assuming that you have multiple things. If you have only one program, then everything would be green, obviously. But in most cases, you will have multiple programs. All right? Any questions? Almost. So the question is, everything else except functional units are kind of double or quadruple in this case. Almost, yes. Things like ROB, you don't need to, because ROB can kind of keep track of things separately. But yeah, typically most things needs to be quadruple.
You're switching each cycle to executing like a different thing for a different program. Like what about instructions that take multiple cycles? Is that information stored somewhere?
Good. So the question is, if some instructions are taking multiple cycles, what will happen? Remember, up to the functional units, things are always taking one cycle. When it goes to the functional unit, then what will happen is things might get, so maybe this would be, so you cannot use, for example, this one. Maybe if this green takes multiple cycle, then this one becomes out of commission for those cycles. You can assign the others, right? But yeah, it's just all this complexity that needs to be handled in your scheduler. All right. So that's kind of like the introduction of multi-core systems. So all these things that we do, we really need to have a multi-core system. I'm not going to talk about it now. Basically, what we will see is kind of like a scenario like this, that we are hoping to see that, we will very nicely parallelize everything, and your programs run one at a time, separately, and you get, if you have n cores, you get n time faster system. What really happens is, because of the challenges that you will see, is that, we're not really using that. There will be some cores that's kind of running faster, and there will be cores that are not running faster. All right. So that's the story that we want to talk about next week and the week after. And that would be the last thing that we want to talk about in this course. There will be some advanced topics that we're going to talk about in week 10, but that wouldn't be part of your quiz. Okay. All right. So final thing about for today is quiz 2. So next Tuesday we're going to have the quiz. As you may have heard, we will have potentially a strike starting Monday, right? For our TAs, for our GRAs, for our postdocs, but not the faculties. I still haven't decided whether I'm going to participate in that strike or not, because technically faculties can also cancel classes. For quiz, let's actually do the quiz on Tuesday, and maybe on Thursday we might or may not cancel the class. Your discussion sessions also, if you remember, this Friday is holiday, so there won't be any discussion sessions. Starting next week, you may or may not have discussion sessions depending on your TAs. I cannot ask them, and I want to ask them. They may decide to participate. If they do, they will let you guys know that there won't be a discussion sessions. If they don't participate, then there will be discussion sessions. All right. And same thing happens to your readers and graders. We are hoping to publish the quiz grades before Monday. If we didn't, and the reader decided to go on strike, then unfortunately we have to wait a little bit more. Okay. But let's keep the quiz 2 for Tuesday. So the quiz 2 is on for Tuesday. just because it just creates a lot of uncertainty for the course. For quiz 2, we're going to talk about, we're going to ask you about 3 different things: the control flow, the branch predictor, and all those things that we discussed in week 4. Was it week 4? Yeah, I think week 4. Then we had all the discussions about out of order execution and, different tables and, how to do renaming, what is it, ROB, what is reservation station, and all those things. Just puts good amount of, practice on the homework. Your question might be something similar to your homework, probably smaller and shorter. And then we're going to have things about your caches. For caches, probably going to ask about addressing. We might give you something similar to your homework where we're going to give you a list of instructions and a cache and ask you to kind of fill the cache. Pay a good amount of attention of what is block offset, what is index, what is set, what is all those things. Also keep in mind that we might ask you about average access time and miss rate and miss penalty, so you might have to compute that. Another possibility is that we combine 2 of these together. For example, a cache and BTB maybe together, or an out of order and control flow together. So that could be another possibility that we might have. What else I wanted to say? There won't be anything about virtual address or anything that we discussed this week, obviously. Okay, so anything that we discussed last time, make sure to watch that video that I recorded about how to optimize miss rate and miss penalty and all those things. And basically look at the homeworks. The 3 homeworks that we gave you would be something similar along those lines. The format would be similar to quiz 1. We're probably going to upload the encrypted version sooner. Those of you who managed to break it last time, good news for you. You can break it again probably. Probably going to be 1 hour to 1.5 hours. There will be some, time pressure. As I said, that's part of it is just intentional. There won't be any lecture before or after, and I won't record anything afterwards. So just you come and take the quiz and leave. You have to be in person like the last time. And don't forget to sign in. The TAs may or may not be here, depending on whether they're decided to strike or not, but I will be here. And then, and then last thing, I think it was on campus where somebody asked, there were a few of you also reach out to me. If we see that you're doing better in your quiz 2 and 3, we might a little bit change the weights of how we, weight the 3 quizzes. So for example, for now, I'm deciding to just do equally 1, 2, and 3, and that would be, I think, 45% of your grade. But maybe if you're doing significantly better in your quiz 2 compared to quiz 1, then maybe we say 20% quiz 1, 40% quiz 2, 40% quiz 3. Still 45% of your entire grade, but how we internally, weighted each quiz might be slightly different depending on your performance. So don't get, nervous if you see lots of questions. Hopefully you can figure it out. And the whole point is for you to learn. All right. Any questions? Yeah. When should you expect grades for first project? That's also being graded right now. Hopefully before Monday. But if things blow up, then you have to wait a little bit. And by the way, your project 2 is out, so go and check it out. It's related to caches, so I definitely recommend to play with it a little bit before your quiz. It would be helpful for your quiz 2 as well. When do we release solutions for this week homework? I think the deadline is Saturday, so we're going to release it on Saturday.